team from Damya Souami. She's a Fulbright visiting scholar from the Observatory of Paris, CNRS in France. She's at UC Berkeley to work with Professor de Potter and her group on the study of Neptune's ring system. She's a member of the DART investigation team and works a lot in collaboration with citizen scientists for amateur astronomers. After a talk, we'll have stargazing today. But first, good morning and welcome.
Thank you.
Hi, everyone. Thank you all for being here. Thank you, Natasha and the team, for all your work. So, as Natasha introduced me, my name is Damya Souami. Before I start, I have to tell you two things about me. One, I get overexcited when I start preparing slides for a presentation. Once I ended up preparing 150 slides. Like, what is this? I'm never going to get the chance to present this. Now I have to downsize. That's too much work. So I did lots of self-control here. I ended up only with 22. So that's one good thing. It was really hard. The other thing is, I just want to say, I don't like listening to monologues nor giving monologues. Therefore, you want to jump in with a question, comment, please feel free to do it. Like anytime. Are we okay? Okay.
Okay.
Great. So let's go to this journey throughout our solar system together. Okay. So quick introduction. I did my PhD in France. This is the boring introduction. I have a more fun introduction coming a bit later. So I did my PhD in France. I worked on asteroids, hence me talking to you today about asteroids. I have many hats, I'd say. I have the dynamicist hat, so theory. I have the hat of the observations, going, gathering data, analyzing that data. And I also have another hat where I do both observations and theory, but this time on rings of planets, in particular Neptune. And I will get back to that later on. So as you can see, I traveled quite a lot, hence my weird-ish accent. Wherever I go, I pick up some things and I ended up with the current accent I have now. So as Natasha was saying, I'm a CNRS researcher. I was hired just this November, and November 1st, my contract started. November 7th, I was in Berkeley. My colleagues were like, I mean, seriously, you are leaving just when you are hired? Yes, I am. So here we are. Okay, so today's talk is organized like this. So first, I'm going to introduce to you planetary sciences. Why is it that we do planetary sciences? How we study the objects that are called small solar system objects. Actually, what are they to begin with? Then I'm going to present to you the future of planetary sciences and how we have the best days are yet to come in our field, both in planetary defense and in planetary sciences. As Natasha mentioned, I work a lot with amateur astronomers, which I like to call citizen scientists, and therefore I will tell you how you can join in. And just to give you a bit of an introduction to that, whatever work we do with citizen scientists, they go, they observe, they collect data, and therefore they are collaborators and co-authors to our papers. So you can end up having your name in scientific paper if you want to. And then I have another bunch because I could not resist to add in something aside. Sticking to my plan is not really my thing, therefore I added an extra item. So first, let's look into this amazing artist view of our solar system. Obviously, it's not to scale. So here, on the left of the screen, we have the sun, and then we have the planets that are aligned. You recognize, obviously, the amazing rings of Saturn. So Jupiter, Earth is here, and you see a swarm here of rocks in between Mars and Jupiter. So these rocks, can you guess what these rocks are? Asteroids, absolutely, yes. So these asteroids between Mars and Jupiter are what we call the main belt asteroids. Because there are many populations, as you will see just in a bit. And you can see here a blue thing which looks like a comet. Could be a comet, could be an object, could be comet from our solar system, it could be a comet coming from elsewhere, as you will see in a moment. So let's go into another representation, another fresco now of the solar system. Well, this one looks, it's not as artistic as the previous one. It looks a bit heavy, but let's take things step by step. First of all, let's talk distances. Before you go to reading things in here, let's talk distances. We are here in this room in Berkeley University. I'm not going to measure the distance from this point to, let's say, the Golden Gate Bridge in inches, in centimeters. I'm going to use proper units, kilometers or miles. Same thing when it comes to our solar system. I'm not going to be measuring distances between planets or between objects in units that we use on Earth. I need to use appropriate units. Therefore, we introduce what we call an astronomical unit, 1 AU. 1 AU is defined, it's not a random unit, it's defined as the average distance between the sun and Earth, as Earth orbits the sun. The average distance over here, that's going to be my 1 AU. That's going to be my unit here when I go through the solar system. This 1 AU is about 150 million kilometers, so that's huge. That's why I'm not going to carry on miles or kilometers out in space and forget inches even exist. And that's about 93 million miles. That being said, well, okay, so I know distance from here, planet Earth to the sun is 1 AU. We agree on that. Now, what about the rest of the solar system? Obviously here, once again, not to scale, because things would not fit in here to scale. It would not be pretty, it would not be easy to read. So here I have this plane here where I have all the planets aligned. So Earth is somewhere here, Mars as well. Jupiter, Saturn, Uranus, Neptune. And so these are the planets. Mercury, Venus, forget about that. They're just way too close to the sun. And then we have all the other objects, all the other rocks, all the other blocks of ice in the solar system that come in different populations. So we mentioned the main belt asteroids. So those asteroids between Mars and Jupiter. But those objects are similar objects exist throughout the solar system. And we classify them, we give them, let's say this is this population. This population is called centaurs. It's here in between Jupiter and Uranus. This population beyond Neptune, I'm going to call them trans-Neptunian objects. I'm going to give them names, classify them depending on how they behave dynamically, where they exist in space. So you see here the scale, it's crazy. It's not linear, it goes beyond and beyond. So we have what we call in this region the Kuiper belt objects. Here we have the Oort cloud. So today we'll be talking mainly about objects that are the closest to us. Closest, again, we'll see what close means. We've seen what 1 AU means. So when I'm saying close, I'm not seeing San Francisco close. So objects that are close here, near Earth asteroids, so they orbit close by to Earth, or objects that are in the main belt between Mars and Jupiter. I will also be mentioning a few objects that are of very high interest, that are outside, beyond Neptune, and more for the future. So here, let's look into this animation. Lots of dots moving everywhere, circling. They're moving in circles. You see this white circle that's supposed to represent Earth on its orbit. The center here is the sun. Then you have the inner planets, Mercury, Venus. You have Mars in the red circle. I'm not sure if you can see it properly on the screen. Jupiter in this yellow arc, and then Saturn, Uranus, Neptune. All these objects are moving fast. Obviously, this is an animation. It's not real. The speeds are not, it's accelerated, it's exaggerated, not properly to scale. But it just gives you an idea of how many of these objects are out there. The objects in orange, yellowish orange here, are representing the objects that are in the main belt. So between Mars and Jupiter. The green dots here, and there are quite lots of them, are what we call the near-Earth objects. So they are orbiting close by to Earth. Sometimes their orbits cross that of Earth. So these objects are going to be, for example, very important for us when we are going to be talking about planetary defense. And by the way, I've been talking too much, so I'm going to ask a question. When I'm saying planetary defense, what do I mean by that, in your opinion? Yes, please.
When I came here, I thought it might be a military thing, but now I'm thinking maybe it's about how to protect Earth from getting hit by asteroids.
Nice. Okay. So I can confirm that it's definitely not military thing. I'm civilian. I have nothing to do with the army, and I'm part of planetary defense mission team. So it has nothing to do with the army. Yes, it has to do with protecting Earth from potential threats. There are no threats for the moment. There are no threats, but potentially preparing in case there were ever to be a threat in the future. Well, hopefully not in the near future, not ever. We would be prepared for that. But that's a good point. And the reason I was asking is because I knew maybe some people would think military. I mean, it's obvious. We hear defense, we think army, all of us. How many, you see lots of objects here in this animation. How many asteroids do we know in the solar system? Could you guess a number randomly?
3,000.
How many?
3,000.
3,000. Okay, that's way underestimated.
5 million.
That's
5 million.
no. I hope not. I hope not, because then we would be outnumbered. To date, we know over 1 million of them. 1 million, nearly 300,000 that we know of. Remember, just because we don't know of something does not mean that it does not exist. These are the ones that we know of. And almost 4,000 comets. And someone said 5 billion. Guess what? We will get to that 5 million by 2030. We're expecting to get there by 2030 because there are new big telescopes coming, new big surveys coming, and we will hit that 5 million and over by 2030. So sometimes you see in the media, an asteroid is passing nearby Earth. I hate those kind of papers because, again, it's passing nearby, close by. How close? What do you mean by close? How do you mean? Be more precise. You are just maybe scaring people for nothing. So it is important to keep in mind the concept of distances that we're dealing with and the numbers. The asteroids have been here for a very long time, since the start of our solar system. They've been here for 4.5 billion years. So we are the new intruders in this equation. They've been here around for over 4 billion years, and we did not know about them until 2 centuries ago. Again, just because I don't know something exists does not mean that it does not exist. So I said earlier, that was the boring introduction, like by CV, whatever you want to call it. And this here is like how I truly want to see my job, how I truly want to see myself. Space explorer and person working from the moon. Well, actually, this one, I was cheating, but well, not really. I was supposed to write my PhD thesis. It was late. I was in the office. It was 11 p.m. or something. I was tired, no inspiration. I just wanted to get home and go to sleep. I'm like, yeah, forget about this. I'm gonna do this tomorrow. Let's play around. Let's go to the moon. So here I was at the moon. So, yes, please.
What's the difference definitionally between an asteroid and a comet?
Thank you. I was expecting that question. Thanks a lot. So basically, a difference between asteroid and comet. An asteroid is basically what you would expect to be a rock. Most of the time, we will see that it's not always a rock as we expect it to be on Earth. However, a comet, when it orbits around the sun, when it comes close to the sun, it's going to outcast, it's going to form that tail. Asteroids won't. There is no ice or not enough ice to actually go to outcast to form that tail. Or another way is to say comets are big dirty snowballs in space. That's another way to say it as well, if you wish.
But they'll have similar, or definitionally they don't have to have different orbits.
Some of them have their own orbits. Like we have what we call, I'm gonna get here, maybe to this one. Some that orbit like this, they're called short period comets, and some that go farther, they're called long period comets. That's an example. And we will see that even in the population of near Earth objects, they're what we call near Earth comets. But they won't be as impressive when they get to the sun as the long period comets, for example. Did I answer your question? Yeah, please.
Well, I think that, my question is similar to hers. Do all comets have highly elliptical orbits, or can they be more circular? And vice versa, the asteroids have highly elliptical orbits.
Well, in the main belt, actually we have both. We have populations that have very circular orbits or close to circular orbits, and we have some that have very elliptical orbits. There are quite few cases. And guess what? That's actually a very good question. Some of them, one of the objects in which I'm working, so we see now they're all orbiting in the same plane. Some of them are like this, going polar retrograde. That's one of the objects which I've been chasing for 3 years, but weather did not allow me to get it yet. But you do get different types of dynamic behavior. And again, for each dynamic behavior, you have a family name. Yeah. I think there was another question. Yeah, please.
Around how many of each kind of comet are circling around of each kind of comet?
So are you saying asteroids? So we think
How
there's
many of each kind of asteroid is circling around?
How many types?
How many? Yeah.
Okay, so these are the main types that we have. So about a dozen, I'd say, roughly, the big classes. But then you end up with inside subclassifying, and you end up with a lot of them. Yeah, please.
so there seems to be a rapid rate of discovery of asteroids. Is that rate consistent of discovery? Because we're at 1.2 now, and we're going to get to 5 million in 7 years. Is that similar with asteroid with comets, or no?
Yes, it is. It is roughly similar. And I will get to the rate of discovery just later on. I have a slide about that, but that's a very good question. Thank you. So out of those 1 million, nearly 300,000 asteroids, only this many, about 15, close to us, I'm not talking about the outside of the solar system, have been explored by space mission. Only this much. These are the only asteroids that have had a space mission either fly by, as in, hello, I'm passing by, taking pictures, or orbiting around them, or probing them, taking samples, or different kind of missions. And obviously, do not even try to read what's written here. I just took this image because it showed all of them. But what's important here, these are not all to scale with respect to one another, but when you see one which is big, it really means it's big. When you see one which is small, it really means that it is really small in space. I'm going to stop by, for example, this one here, Ida, and Dactyl. This was the first asteroid. This was the first asteroid. This mission was Galileo mission, a NASA mission. The first satellite of an asteroid was discovered through this mission, we realized that asteroids can have moons. Interesting. How many of them can have moons? Is this a rule? Is this an exception? And nowadays we know many, many moons of asteroids. For example, let's say, I'm not going to go to all of them. Some of them I'll be mentioning later on, but let's take this one here. This one is the biggest in the main belt, Ceres. And this one is the second biggest, roughly half of Ceres. And both of them were explored by the Dawn mission in the years 2010. So I'm saying big. How big? What do I mean by big? I mean, we all understand now that in terms of distances, I have to adapt. I'm saying big, how big? I'm going to compare it to something we know. So here's the map. I hope you see it properly. So we're plotting France, since I come from France, over the US. Obviously, it looks small. It is small. But when you look at the map of Western Europe, it's actually the biggest one. So, so just stating point, I mean, I cannot stop saying France is small. I have to say something else. Now, when we compare Ceres with respect to this map, all to scale.
Wow.
I did not dare to put Ceres on the map because I would be covering France, and I don't want to. I don't want to have home to go back to. But the point is that it is as big as France. This is the biggest asteroid in the main belt. Just to understand what we're dealing with, and later on we'll be seeing things which are much smaller than this. Yes, please.
So Ceres is considered an asteroid and a dwarf planet at the same time?
Thank you for your question. Actually, so he's asking whether Ceres is considered as an asteroid or a dwarf planet, or dwarf planet at the same time. So you all know that Pluto is no longer considered a planet. So it was demoted to the rank of dwarf planet, whereas Ceres went from asteroid, was upgraded to the rank of dwarf planet. So I'm saying it's an asteroid because it was for 200 years, but actually now it is a dwarf planet. My point is that the reason I've been actually waiting for this question. The reasons I'm referring to it as asteroid, and now we all know what a dwarf planet. Well, we don't know what a dwarf planet is, but we know that it is a dwarf planet, is because it's in the main belt asteroid, and it's the biggest object in that asteroid belt. That's where we'll stop. We'll not go to the technical details. Now, I've been talking about asteroids. I said I talked about comets. One other way for us, one other generic word for us to put all these objects in the same basket is just to say small solar system object. That's very generic. You can put everything into it. Everything fits in there, except for planets, obviously. But you can put all of the other stuff in there. Now, when I tell you asteroids, what's your first reaction? What's your first impression, your first feeling? Are you scared? Are you fascinated? Are you curious? Are you something else? You don't care? It's just a rock in space. You're also allowed to. No? No reactions?
Look for the ones that are gonna hit you.
Yeah. Why do you want to look for those who are going to hit you? Yes, please.
How big would you say was the one that took out the dinosaurs?
Aha, so you're going to the dinosaurs.
That one.
Okay. About 10 kilometers inside, roughly between 6, maybe a bit more, 6 to 8 miles in diameter. But that's a good question. So he went directly to the dinosaurs. So he is a bit scared that the same thing might happen to us. I'm just gonna, there is just a question there. I'm gonna get back to you. Yes, please.
Is Ceres that actual shape? Like, is it actually round or is it?
It is.
Really?
Yeah. And that's why it was upgraded to the rank of dwarf planet. because it's like a big sphere.
Would anybody consider it a moon?
Sorry?
Would anybody consider it a moon?
No, it's not a moon because it's orbiting around the sun. It's not like a moon is attached to another object which is not the sun. This one is actually just living its life around the sun. Yeah. Yes. Please.
Okay, it's big, the asteroid that wiped out the dinosaurs, supposedly.
Yeah.
It's big, but it's not really big.
It's not huge.
So how did it
That's correct.
wipe out?
Okay.
everything?
That's a very good question. So it's not okay. I hear some nice vocabulary, aftershock. Okay. Very nice discussion here between two young planetary scientists. No, I really like your discussion. Okay. So the thing is that he's saying if that asteroid that obviously hit and led to the extinction of dinosaur, it does not seem that big. How come it led to that? It's not all about the size. There's also the speed at which it hits. I mean, if I drop, well, I won't drop my phone. although I could gently drop my phone, or if I throw it really hard, it's not going to be the same effect. So it's the same thing. So other reactions. Okay, this is how I think most people would react. Obviously, there is asteroids here. There is the fascination. It's fascinating. Some people are interested. What are those rocks doing there? I mean, what are they supposed to be? What are they? Where do they come from? Some might be saying, I'm curious, yet I'm scared. What if I end up like the dinosaurs? I don't want that. Others would think, you know what? I'm going to get there. I'm going to do asteroid mining. I'm going to be rich. That also exists, although that has fallen apart because it just costs too much money for zero profit, quite the opposite. And then the part of science, which I do, which is I want to understand things for the way they are, but also to answer other people's questions, to reassure them, to answer their so that to show them that they have no reason to fear. And for that, there is obviously pure science from Earth, there is space exploration. And eventually, if there is some threat, then we will be preparing for that with planetary defense strategies. Another thing that you mentioned is the dinosaurs. But you know what? Asteroids hitting Earth does not always mean the end of life or 2/3 of life. It also, asteroid hitting Earth, that's how the elements that were at the origin of life came to Earth. So they're also source of life on Earth. It's thanks to the asteroids that we have life on Earth. They delivered what's called the prebiotic material. So that material which is necessary, crucial to the formation, to the development of life on the planet. Yes, please.
What defines the size of a dwarf planet to an asteroid? Like, how big does it have to be?
Okay. So that's a very good question and very tough. So what is the size that would say, okay, this object is a dwarf planet, this object is an asteroid? Size is important, but not just size. Not just size. It has to be big enough to the point where when it formed, it became like sphere shape, spherical shape. So it cannot look like potato-ish object, as I like to say. You've seen some of the objects that I showed earlier, they had weird shapes, like potato shape, wherever. I like to call them potato-ish because I love potatoes, but you call them wherever you want. So there is that. And that was the case for Pluto, and it's also true for Ceres. The committee that actually, the International Astronomical Union that defined this convention, they said it has to clear the orbit, to clear its orbit. So there should not be thousands of objects close to it.
Okay.
And Pluto see many objects, thousands of objects were discovered around it as well, just like in the asteroid main belt. And they're called Plutinos, because they're followers of Pluto, if you wish. But the point is that there is that part of the definition as well. It's not just the size on its own.
So they have to have their own orbit path.
That their own orbit path, which they clear, they dominate over that path. And they're big enough that they're spheres, not just any random
Yeah.
shape. Yeah? Okay. So just following time, oh gosh. So what science, how we do our science? So we have observations, gather different types of data. So we study basically how these objects are distributed, how they are spread around in space. So basically their positions, their composition, are they metallic? Are they formed of carbon? Are they formed of something else? What kind of material actually composes these objects? Their masses, how heavy, how massive are they? Their sizes, small, big, shapes. Do they have mountains? Do they have craters? For example, Ceres, which I mentioned earlier. So the second biggest object, the one just after, Vesta, the second one. If you scale it to the size of Earth, in its south pole, there is a huge crater, which would be the size of the Pacific Ocean. That just tells you how big these things are. So there are mountains, there are craters, there are valleys, there are all of these topography landscapes on these objects as well. Do they have moons? As we've seen, some of them can have moons. Do they have rings? That's a weird question. Some of them have atmospheres as well. So I'm going to gather all these types of observations, and I'm gonna get. I see some skeptical faces. I'm gonna get to that in a bit. I'm gonna answer your question. If I don't, get back to me. We're going to use multiple methods for that, multiple tools that we have. We have, for example, space missions. I put here some of the latest space missions. NASA New Horizon, maybe you heard of this mission? A couple of years ago, or in 2019, January 1st, it sent us an amazing image. Happy New Year from outer space. Here is an image of an object, which is called Trans-Neptunian Object, AROCA. Here I'm going a bit fast because I realized that time, yeah, sorry for that. Hayabusa 1, which is Japanese JAXA being the Japanese Space Agency, Japanese mission, and Hayabusa 1 it just blows your mind how the Japanese did it. They went to an asteroid, they collected sample, and they brought back that sample to Earth. They did it not once, but twice. They had the Hayabusa 1 and Hayabusa 2, and both samples are on Earth. Both samples are on Earth, and we will receive actually in a few months, the sample from OSIRIS-REx mission, the first one, NASA, Canadian Space Agency, CSA mission. In the meantime, the Japanese did too. And they were the first one to actually, they went crazy. They took risks. They took lots of risks, but amazing risks, amazing results. Then there is the Rosetta mission. ESA is European Space Agency. So it went to study a comet. It followed the comet for years. It studied the comet and it sent us amazing results. Again, sorry, I'm speeding up a bit because there are some exciting things I want to talk about later on. We have space telescopes. So we have the Hubble Space Telescope, which you have probably heard of. It's been giving us amazing data since the 90s. So over 3 decades of data from the Hubble Space Telescope. And there is the James Webb, which you have seen in the news. You have seen many press releases with amazing images coming from there. And we have ground telescopes. So the big ones, the gigantic ones, like the VLT. Yeah, one thing I have to tell you about astronomers is that we're not that great with giving names. We lack imagination. Like VLT stands for Very Large Telescope. and actually the next one, the future, the replacement, our next generation, at least from the European side, is because this is VLT is the European Southern Observatory in Chile. Next one will be the ELT or EELT, European Extremely Large Telescope. Yeah. As I said, like imagination, no, why not? There is the Arecibo Observatory in Puerto Rico. It's radar observatory. It's amazing. I mean, I was there 2 months ago. Obviously, the antenna has fallen now, but it's just amazing. It's a legend. And even if the antenna has fallen, I have to be there. This is history. This is where science, amazing science, was made. Then there is the Keck Observatory and many others in Hawaii, in Mauna Kea. And I chose to cite Keck because UC is highly involved in it. It's UC NASA telescope. So University of California is there. And I'm actually working on data right now here in Berkeley on data that comes from the Keck telescope to study Neptune. And then we have the small telescopes. Do not underestimate them. Please respect, and I truly respect the people who use small telescopes because they are still able to do some amazing science out there. And you will be using some of the telescopes that are the same type of some telescopes that actually led to amazing discoveries. So do not underestimate your small telescope. It can still do some amazing science. Now, once I have all of these telescopes, all of these instruments, space missions, whatever, what am I going to do with all this information? Why am I doing that to begin with? I'm not just throwing away money. I'm doing things because they have meaning. All these measurements, I'm going to use them to inform my models, my numerical models, my numerical simulations, or my theories. Why? What models am I going to inform? How did these objects form? How did these objects come to be? How are they? Why is it that we have these different populations? What are the differences between them? And one very important question is, how did our solar system come to be? How did it evolve? And maybe something I should add is that these asteroids, these rocks in space, wherever you want to call them, they are the leftovers from the early stages of the formation of our solar system. Therefore, if I want to understand the very, very early ages of our solar system, I should go to those rocks. I should go get as many samples as I can. I should use as many methods as I can from the ground, from space, to study them, to see what are their compositions, what are their dynamical behaviors, etc. Because this will help me inform the models of how did our system come to be. And remember again that they are at the origin of life on Earth. So understanding how planets were formed, in particular, understanding the origin of life on Earth, developing planetary defense strategies so that we can have our own shields from whatever is coming our way in the future. You mentioned earlier something about number of discoveries of the asteroids, and I told you I'd get back to you. Here we are. So here, we're now going to talk about the future of planetary sciences, the future for studying asteroids, and it's a very bright future. What you can see in this graphic here is how the number of discoveries of the near-Earth objects, so the ones that are the closest to us, that their orbits sometimes cross the orbit of Earth, how many of them were discovered over the years, over the past four decades. You can see that in the 80s, there were nearly 0. And now, see the number here? We're at over 30,000 objects in total. Over 30,000 objects. And guess what? We have not even discovered, we're not even close to having discovered all of them. At least for the bigger ones, the ones that are more than 1 kilometer in size, we're sure that we almost got all of them. However, the smallest ones, we're still missing a lot. And we will have to chase them to track them before it's too late for us. Yes, please?
What are the 3 colors that you need there?
Yes, I was gonna get there. So the 3 colors here, what you see here in the red, and there are very, very few. Someone asked me earlier a question, I think it was you, about comets. So in red, those are near-Earth comets. There are very few of them. In blue here is just the total, the cumulative number of everything, adding up everything. In orange, what we have here is what we call the potentially hazardous objects. They are potentially dangerous. I will get back to you. Potentially dangerous, but when I say potentially hazardous, does not mean that there is a threat right now on Earth. It's just that they are big enough. I mean, I would not take the risk of them being too close, therefore I'm going to monitor them closely, because if they were to hit us, it would be very bad. Therefore, I'm going to monitor them closely. They're more than 140 meters inside. I'm going to monitor them closely, just being safe. Better safe than sorry. Yes, please.
How many of the comets are, how many of the comets are inside each group of some kind of comet? How many comets?
How many comets? I can
inside each kind of comet.
Okay, I cannot give you an exact number, but all I can tell you is that the comets that are near to Earth, there is for now that we know of 121 that we know of today, as of today. But maybe next week it will change. Maybe by next year it will change that number. But for now, this is what we know for near-Earth comets. And obviously I said better safe than sorry. And for that we have missions, we have telescopes that will come in the futures, like the NEO surveyor, which will be launched in 2027, which will be dedicated to detecting the smallest near-Earth objects. That will be its mission. Go out there and detect the smallest one, because they're too small, too faint for us to see them in advance, and I want to detect them as early as possible. And obviously there is this Vera Sloban Observatory, which will actually see its first light, so start being operational next year. And this is an artistic view, but obviously the Vera Sloban Observatory is not dedicated to near-Earth asteroids. It will detect many, it will do astrophysics, it will detect many objects. But in terms of asteroids, it will be detecting lots of them, and not just the ones that are close to us, even those in the outskirts of the solar system. Because for now, I've been talking a lot about those that are close to us, because those are the ones for which we had many missions. Those are the ones which we know the best. Another thing is there are some other remarkable results. And I'm just gonna check the time. Well, I'm gonna go fast. So this here is asteroid Ryugu, which was visited by a JAXA space mission, which went there, collected sample, and returned it to Earth. So you will see here this animation, how it's going to collect the sample, the arm. You see how it will hit the surface of the asteroid, and this is accelerated, obviously. Puff, you see dust everywhere. This video is really accelerated. It went really, really slow in space. This is low gravity. Just a second. And it collected the sample, and that sample is 5.4 grams. I mean, you might think, yeah, 0.2 ounces. What's this? That's nothing. Yeah, it might seem like nothing to us, but in science lab, that's a lot. In science lab, you can do a lot with that. Yeah, please.
Is the machine that gets those samples controlled by people from the ground or in space, or is it controlled by a robot?
Okay, that's a very good question. Actually, it's purely autonomous. It's been programmed that once you get there, you are around target, then you are on your own. You have to figure out how to do things on your own. And that would be the same thing for the DART mission. We'll be talking later on about that. Yes, please.
What's the method of mapping those objects? Motion.
There are many methods involved. You mean mapping the surface or mapping the motion of the objects?
No,
the whole thing. So what we do is that we measure we observe, we detect their position in the sky, and we measure, okay, at this time, this day it was here. At that time, it was there. At that time, it was there. And then we fit an orbit. And that's the thing, is that these potentially hazardous asteroids I was mentioning, at first, when you have 2 or 3 points that you detected, you can fit nearly anything. When you have 2 points, you can have a line go there, a circle, whatever, an ellipse, anything that goes, like any curve you can fit by 2 points. The more you get, the more points you get in space, the better you know your object, and your uncertainty becomes smaller and smaller. And that's how it goes from, this is a very scary asteroid. I observed it twice, and it's gonna hit Earth. I'm sure about that. And then you observe it 3rd time, 4th time, 5th time. Yeah, whatever. Forget about that. It's not dangerous. So that's how it goes usually, the process. And that's actually my bonus thing is actually about that. Then I'm going fast here because I could have spent lots of time talking about Hayabusa, but now talking about first planetary defense mission. So you mentioned earlier that now we understand that it's not military, it's about preventing any hazards on Earth. I actually this morning, I'm like, yeah, I have to wear my DART mission. I'm a member of the DART team. So DART stands for Double Asteroid Redirection Test. That was the mission, the first planetary mission by JPL, led by JPL. And there was a big international team, and I am a member of that team. So basically, the idea is to deflect an asteroid, change its orbit. An asteroid is coming towards Earth, I'm going to smash into it, push it into another orbit. But we're not obviously going to try that on a real asteroid that's possibly dangerous, on dangerous course to Earth. We're going to go and hit a poor one, which is not representing any danger from us. And we see there, it's scared. That's not fair. Yeah, absolutely, it's not fair. I'm sorry for that. So what we went to a near-Earth asteroid called Didymos, which has a moon. So at first they were called Didymos A and B, A for the big one, B for the small one, by our American colleagues. In Europe, we call them Didymae and Didymoon, which I preferred. And now they have proper names, Didymos and Dimorphos. So the mission went and smashed onto Dimorphos to change its orbit with respect to the orbit of the system, so that we're not taking any risks. It's a safe mission. So here you will see the animation. It's going on through, and then puff, it's smashing onto Dimorphos. So here again, repeating, just plain and loop. You see it's going through the 2 components. This is obviously accelerated. In space, it did not go this fast, except when it almost reached the asteroid. So this, at what speed was this impact then? At 6.6 kilometers per second. So that's 4.1 miles per second. I mean, I know, again, earlier I was saying 4 grams, it seems small to us. This seems huge to us, but this is typical of the collisions in the solar system. So it's normal speed, like it's nothing impressive. Things happen in solar system collision between asteroids at much higher speeds than this. So just to compare, earlier I compared Ceres to the US and France. Now let's compare the 2 components, Didymos and Dimorphos. So this is again from the DART mission. So I have a bus here. Then we have the DART spacecraft, basically that thing which went onto the asteroid. It's the size of, say, washing machine, and weighs as much as a bus. But when it deploys the solar panels, it goes to about 19 meters. So we have the Arc de Triomphe monument in France, the Statue of Liberty, and Dimorphos fits here. The poor little guy said, that's not fair. It fits in here. You have the pyramids, the Eiffel Tower, One World Trade Center, and Didymos, which is much bigger, but again, still under kilometer in size. So these shapes here are for Didymos, we had radar data from 2003 that gave us more or less the shape. From Dimorphos, the satellite, we inferred its shape from data. We never saw it before, but we inferred its shape from different other measurements. And it turns out that when DART got there, they were slightly smaller than expected. As for the shape of Dimorphos, it was completely unexpected. And that's what we love about science, is the unexpected. Expect the unexpected, otherwise there is no point in doing science. So here, these are DART images. So this one, 11 seconds before impact, these images were taken from Draco, which is the camera on the spacecraft on DART. So 11 seconds before impact, from 42 miles, 68 kilometers, it saw this. It captured entirely Dimorphos. Obviously not what we were expecting at all. You can see here many boulders on it, pebbles, whatever. Again, not expected at all. And 2 seconds from impact, this is what you see on the site of impact. So accelerated, but that's how it went. And that's how we end up with that plume of ejecta. The point is that these asteroids, when you look at the images that I've shown earlier, are these ones, you think it looks like rock, whatever. But sometimes when you go and hit on them, you end up with, just like we've seen for the Hayabusa mission, you end up with lots of dust coming. It's not a rock. It's more like, let's say, pebbles or boulders aggregated like sand. You know how sometimes you have sand that looks like hard rock when it's actually, you just take it and it falls apart. Some of them actually are much closer to that than to being rocky objects. Basically, what happened is that we have Dimorphos here, Didymos, DART, which is an APL mission, came here. It separated. There was an Italian CubeSat, small CubeSat, which was integrated with the DART. 2 weeks before it separated, it observed the impact. So it smashed onto the asteroid. So this was the old orbit in white, and now we have the blue orbit, the new one. And we were able to measure the change in the orbit. So it was a huge success for a first planetary defense mission. That is an amazing effort of an international team which has been working for years, and 2 years of Zoom meetings and lockdowns and whatever, we made it through. The team made it through, and we ended up with this amazing mission. And guess what? It's not over. Because yes, we did smash into it, we did change the mutual orbit, but we want to study more. We want to know the size of the crater. We want to know exactly what is the density of these components, what are the masses, etc., etc. And for that, we have the Hera space mission from the European Space Agency, ESA, which will be launched next year, which will go there and study the aftermath of the impact. So the experience is not over yet. We still need to measure what we have done, what we have accomplished. Now, go farther from Earth, getting farther away. Yes, please.
One question, so if the asteroid is more loosely packed, would it be safe to assume hypothesis that if that were to be on a collision course, it would more likely burn up in the atmosphere or cause damage and put the density back?
There is no atmosphere here.
Oh, if it would crash there.
Yeah, okay. If it would, could you please keep that question for a bit? Yeah, okay. Just going to go a bit, I'm gonna go fast. I know, Eli. So outside of the solar system, we have other objects, as we have seen earlier. But before I talk about those other objects, do you know how many ring systems? I'm jumping from one topic to the other, just like big jump. Do you know how many ring systems we have in solar system? Yes, please. 2, 3, 3. Okay, what are they? Yes, please.
4.
4. Okay, what are they?
Jupiter, Saturn, Uranus, and Neptune.
Okay, great. So all the 4 giant planets have ring systems around them. Jupiter, Saturn, Uranus, Neptune. That is correct. But guess what? Some rings were discovered around some of the small solar system objects as well. And that shows that when you think you understood something, something comes your way and no, actually, I did not understand anything. I'm not close to understanding anything. So these are the 3 ring systems that were discovered around small solar system objects. So the Centaur-Chariklo, so between Jupiter and Uranus that it orbits, these here are 2 trans-Neptunian objects. They are dwarf planets, as you mentioned earlier. And this is fairly more or less to scale with respect to the rings of Neptune. So these are the 2 main rings of Neptune. This separation between them is about 6,000 miles. And here, these systems are roughly to scale. So we can see that different types of objects throughout the solar system, we have centaurs, we have dwarf planets, they also have rings around them. And that's really puzzling because that definitely was not expected. And when you look into the details of these rings, that's even more, you think, no, come on, I'm not going to destroy a theory that's 200 years old just to fit this ring. But actually, no, you're not going to destroy it. It's just that theory is incomplete and you have to work to complete it. So basically, and I'd like to insist on this, how we detect these objects, how we detect these rings. And that's where you come, if you wish, and that's where the components where we have been working with amateur citizen astronomers is basically you have a star in the background, you have many stars in the background, and you have small solar system object. Let's say my phone is an object that's going to pass here, block the light of the star, and pass again, and then we see the star. So I'll be measuring that. I'll be measuring the disappearance and the reappearance of the star. Puff, little blink. There was something. Now it's off completely. It reappears. And another blink. That's weird. I just detected the rings. I just detected the rings around an object. And actually, these detections, most of them were done using small telescopes, like the ones you will see on the roof. Small telescopes that belong to amateur astronomers, citizen scientists who work with us. So you can be one of those if you want to. And this method, by the way, is called stellar occultations. Star being occulted, star being hidden for a moment. And basically, the amount of precision, how accurate my measurements can be. Let's say, well, we are here in Berkeley. Let's say we know someone who is in San Jose, and we know another person who has a big lamp, which would be a star, in Sacramento, and they have this nice stamp, which was issued last year by the US Postal Service. I'm making some publicity for them, which is a stamp from the James Webb Space Telescope. Actually, I'm making publicity, but they are sold out. I went yesterday, they said they are sold out, but never mind. So the point is that let's assume that it's all flat all this way. From San Jose to Sacramento, it's all flat. No, Earth is not curved. There's no mountains, no valleys whatsoever. So with my telescope, the amount of details I'm going to be able to recover using stellar occultation is that I'm going to be able to measure the indentations of these stems, which is here, and I'm all the way here. This is the amount of details that you can contribute to science with your small telescopes that you absolutely should not overestimate. And earlier, I think that was you asked me something about a question that led me to thinking about this. So, Apophis, have you heard this name? Yes? Yeah, please.
Is it an asteroid that's supposed to then come around like 2029, and then it might, if it goes through a certain spot in space, it might come around again or something?
Okay. And another person behind you, you've heard of No? Okay. So it's an asteroid, which is going to come by close in 2029, indeed. When it was detected, I remember now your question, when it was detected in 2004, there were few points detected in space. This is today, I'm seeing it here, tomorrow here, day after here, etc. And it gave a big scare to the community in the Christmas of 2004, because they were seeing the trajectory leading to an impact with Earth in 2029. It was going to be a disaster, because this one is PHA. It's 340 meters in diameter. It's not those 140 I was mentioning earlier. So as people gather data slowly, they realized, yeah, no, 2029, whatever, it's gonna come by, say hello, and we're just gonna live through it. There's no danger at all. But see those first points, because you don't have enough points, you are scared at first. But as you get to monitor it closely, then you think, okay, but if there were danger, you would react. Because if you detect that in 2004 and you know it's going to be in 2029, you have 25 years to react to that. And that's where those planetary defense strategies come in place. But my point is that it passed close to Earth. So these are radar data. Some of them are actually, some of these data come from the Goldstone Observatory. So here in 2029, this is Earth at the center, and this in white is the orbit of the moon, our moon, which you will see tonight in the sky. It's near the full moon. And Apophis is going to pass this close to Earth. It will be 10 times closer than the moon. It's going to be amazing. We will see it in Europe, in Western Europe, and in North Africa with a naked eye. So if you want to see something this amazing, which happens only every 1,000 years, April 13, 2029, be in Western Europe, be in Northern Africa, you will see it. Yes, please.
You know how bright it's going to be? Like you can see it with a naked eye.
You can see it with naked eye. Yeah, it's not going to be amazingly bright, but you can see it with naked eye. Yes, please.
When was this named, and was it before they realized like that actually wasn't going to destroy the Earth?
When it was named afterwards, obviously. It's you need enough data. At first, it was just given a number, 2004, wherever, because it was discovered in 2004. But it was named much later, after you know properly its orbit. I know you are probably referring to the name Apophis from the Egyptian mythology, which is basically associated with chaos. Yeah. Yeah. No, but no worries. It does not. And actually, in 2020-21, it passed close to Earth, when again, close being like not that close, it's 10.6 million miles, but you will see everyone excited. Yeah, it passed really close. It passed close enough for us to get radar data and some amazing occultations. Remember that disappearance and reappearance of the star I was talking about here. Well, each one of these lines, each one of these ports, a moment where the star disappears, the moment where the star reappears, the moment it disappears, it reappears from different observers. And this observation was done by observers here in the US. And it was the very first time that we got an occultation by an object this small. So it was, again, do not underestimate your small telescopes. That's my point once more. So here are the main outcomes. Small solar system objects are witnesses of the birth and the evolution of the solar system. There are multiple types of SSOs with multiple sizes, shapes, compositions, etc. They deliver the early material that gave life on Earth. They are studying as solar system objects is key to understanding how our solar system came to be, how it formed. And we end up having the first, and I'm proud to say that I somehow participated with my small participation to the DART team, which led to the first successful planetary defense mission. And remember, there's the second part, Hera, which will go and study the aftermath. It will be there by 2026. There are lots of exciting missions to come. over the next few years, basically one amazing thing, at least per year, until 2030. And here's my email address. One more thing, Asteroid Day, June 30th, every year there's Asteroid Day, and there are big, there are some events everywhere on Earth. There are some events in San Francisco, some conferences you can attend, and you will learn a lot about asteroids, and basically you will learn more about the things that we discussed today. And as I'd like to say, the best is yet to come. And thanks again for your attention. It's very helpful.